So today we began our set of proofs that the transformations that we've seen so far, which are translations, rotations, and reflections, we began the proof that each of those is in fact an isometry, according to the original definition of isometry, which you'll recall is that a transformation is an isometry if it preserves distance. In other words, for any 2 points that I choose in the plane, the distance between them has to be the same as the distance between their images. So if you and I are 5 meters apart and then an isometry happens, then we need to still be 5 meters apart afterwards. That's what the isometry definition is. So we start by showing that the translation, which is defined by a directed segment, a specified directed segment, is in fact an isometry. And so what was done here is that we select a fixed segment PQ and use that segment PQ to define a translation, and choose 2 arbitrary points, A and B. So here's A, here's B. And then define their images under this translation, A prime and B prime, according to the definition of translation. And the definition of translation states that A prime has to be congruent in the same direction as and parallel to the segment PQ. So we get a parallel segment that is also congruent to PQ. And likewise, when we define B prime, the translation of B, we're also saying that that segment is parallel to PQ and congruent to PQ. But by the time we've done that, what we find is that A prime and B prime, by the transitivity of congruence and parallelism, are congruent and parallel to one another. And because they're congruent and parallel to one another, we can say, and this is the big kicker, that A prime, B prime is a parallelogram. Because you'll recall that Theorem 2.3.5 guarantees for us that having one pair of opposite congruent parallel sides is sufficient to create a parallelogram. Therefore, since this is a parallelogram, we can also deduce by Theorem 2.3.1 that the other pair of opposite sides are also congruent. Namely, AB is congruent to A prime, B prime. And that shows for us that this transformation has preserved distances and therefore is an isometry. Having shown that translation is an isometry, we were also able to show that rotation about a fixed origin O through an angle alpha is also an isometry. To do that, we went back again to the definition of how to apply a rotation, definition of what a rotation is. So rotation is defined by the property that any point P rotated through this fixed origin O to a point P prime will have the property that, first of all, PO is congruent to P prime O, so we haven't changed the distance from the point to this fixed origin of rotation. And also that any 2 points which are so rotated, so if I also introduce a Q here, it's rotated point Q prime. Likewise, QO has to be congruent to Q prime O. And so now as when we bring the angle into the conversation, the angle of rotation has to be the same for the points P and Q. So the angle PO P prime, if we call that theta, is congruent to the angle QO Q prime. Right? So those have to be 2 congruent angles. And so how we're able to argue in this proof is that the congruency of the angles theta that are both labeled on this diagram implies the congruence of the angle POQ and the angle P prime OQ prime by envisioning both of those angles as making somehow the difference in between theta and the angle POQ. So if we argue that those two are congruent angles, then what we find is that we can make a congruence argument for the triangle POQ and the triangle P prime OQ prime because of side angle side. So one of our sides is the single congruence mark hash, then our angle is the double congruence mark hash, and then our second adjacent side is the double congruence mark hash on the side QO. So according to that side angle side argument, POQ and P prime OQ prime are congruent triangles. But because they're congruent triangles, the segments opposite congruent angles are also congruent, and therefore PQ and P prime Q prime are congruent segments, because they're opposite that congruent angle. So that's a great proof, but then my caution on this is that the diagram and the reasoning might look a little bit different if our angle of rotation had a different comparison with the angles in between P and Q. So my caution was that if my angle of rotation were very small, in particular if it were smaller than the angle POQ, then arguing that that angle is the difference between theta and POQ is going to make a slightly different it's going to make a slightly different algebraic form of this argument than the one that we had. It's not going to make a difference to the reasoning, but it might make a difference in how some of the stuff is written. So the general caution here is that when you draw a figure, try and see if you can draw it in a different way that leads to a different line of reasoning. I'm not going to let that stand in the way of this proof, but it's sort of a general caution in drawing a figure to argue a proof in geometry. We'll see the proof for reflection at our next class.